My name is Paulo Moura Oliveira. I'm going to present a paper entitled Entropy-Based Gray Wolf Optimizer. This work was done by Daniel Duarte, is a master student, and also with the collaboration with Eduardo Pires. So, the motivation for this work is the following. We have plenty of algorithms that seek inspiration in the natural phenomena. These algorithms have been growing in importance, and one of these algorithms is the gray wolf optimizer, GWO. It is one of these many algorithms that has been inspired in nature and has been successfully applied to solve problems. So, since his original proposal by this reference by Juan Birlacci, several refinements and variants were proposed. You can see this reference here. One of the problems of the GWO is that it suffers from premature convergence. Premature convergence is closely related with the swarm or population diversity. So increasing the swarm diversity will decrease the premature convergence problem. So here in this paper, we propose the use of the channel's entropy into the GWO algorithm to track the swarm diversity and thus improve its performance. How does the GWO works? So its inspiration is in the gray wolf pack. So we have four main categories of wolves: the alphas, the betas, the deltas, and omegas. So this is like the pyramid for the hierarchy. And so the best element in the swarm is assigned as an alpha wolf. The second best is the beta, the third best is the delta, and all the others are omegas. So the dynamics are represented here, and you can see more information in the paper. We got a kind of encircling technique where there is a prey position, and this is the wolf position. And this prey actually acts in the optimization problem as a kind of maximum of minimum, local optima. So we can actuate and update the position based on the prey position using this subtraction here. And we got here this parameter A is the parameter which is responsible for the search, exploration, and exploitation compromise. So for the three higher ranks, these are the dynamics for updating the Ds. And then we got the updating of the X1, X2, and X3. And we average these position values. And this average is the updating for all the wolves positions. Okay. So the algorithm is quite simple. We got the first, we initialize the population, then we initialize the parameters and also the A, and then we got a loop with repeated until our termination criterion is reached. So we evaluate the swarm, update the positions, and so on. So this is quite easy to do. Then we get the Shannon entropy. The Shannon entropy has been used in information theory, and it can be used also, and has been also in several natural inspired algorithms to track the population diversity. You can see the paper for more reference about this. So what is the idea behind the entropy-based gray wolf optimizer? So we are going to use entropy to track and compare the distance between the alpha wolves and with the beta and delta. So based on this distance and entropy, we are going to evaluate if the swarm doesn't change much. I mean, it means that it gets stagnated. If the distance and the entropy doesn't change for a certain number of iterations, we assume that the search is stagnated, and we restart the swarm positions. So this is the algorithm. So the algorithm is more or less the same one, but with the difference that in the middle, in the cycle, we evaluate and store the entropy values. And if this stagnation criteria is reached, we restart the swarm positions. So we got here some simulation results obtained with some benchmark functions that Midlachi used in his original paper. And we can see here for F6 function that you can see the details in the paper, the performance between the best value achieved by the GWO and also the best achieved by the entropy GWO. You can see that the entropy is the one in the bottom, is better. So, and also this is due to for what happens to the average values. You can see these spikes here. These spikes here corresponds to the population or swarm reinitializations. So, to avoid that these reinitializations happens or occur frequently, we have a minimum value, it's a kind of Bose value that we avoid a minimum number of iterations that avoid restarting the swarm so much. So with another function also we can see that the entropy GWO behaves better for the best value and also for the average values. The same thing happens for the function F12 and also for the function F13. So overall, we can see also in the table the results that in the paper. These are two tables that you can check in the paper. And in most the best, worst, mean, and standard deviation for most of the cases, the EGWO performs better than the original value algorithm. Sorry. So as a conclusion and further work, Shannon entropy was incorporated into the Gray Wolf optimization algorithm. The resulting algorithm was tested and compared favorably to the GWO in 8 benchmark functions. The proposed algorithm requires adjusting the swarm restarting threshold as well as the minimal pause period. These are two additional constraints that have to be adjusted for the specific problems. And of course, more research is necessary to try to devise an adaptive mechanism to automatically determine how should the entropy GWO be restarted, okay, and what should be the threshold for. Okay, so this concludes the presentation. Thank you very much.